So in this example, we will look at quasis analysis of a particular set of samples. We find the data, the spectra, in this folder, number 8 down in the list here, but we have 3 spectra here from, these are all gold 4D of 3 samples. The first one, gold is deposited on nickel, so the gold on top of nickel, and then we deposited nickel on top of that in various amounts in samples number 2 and number 3. We start with the first one here, click this, click buried layer, and we want to analyze this. To do that, we need to put in an IMFP. For that, we can use the Quasis IMFP calculator here, which is based on the TPP2M formula by Tanuma, Powell, and Penn. So this is a very convenient way to determine the IMFP. In this case, we have gold, where we have a lot of examples here, a lot of different materials, and you can choose any one of these and find the IMFP. You can do a non-relativistic, relativistic, or relativistic calculation. Normally, at the energies we're working at, the non-relativistic case is sufficiently accurate. You can also find the material by just typing in here and look for it. Now we have gold loaded here, the parameters for gold, and what you do is you look at the spectrum here and you find the energy. It's about 1150. You can vary it here, see the variation in the IMFP. We take 1150, that's 13.6, so we put that in here. And we have the angle of emission. We have normal emission in this case. You have the choice of inelastic cross sections. You would use this a list here of cross sections, and you can also modify cross section and create cross sections yourself. We'll return to that in another video, but your first guess would always be the universal, unless you know you have a polymer or you have some silicon sample. So in this case, we use the universal cross section and we analyze this. So now we expect gold to be on top, and clearly you see the background gets better when I move this closer to the top, and we have about 13 angstroms on top of the structure. You can vary this. You can see it's clearly not this, it's clearly not that either. You can change the increments here that you get by hitting these over here. So if we take an increment of 1, we can still see that 1 angstrom is too much here, and 1 is probably the uncertainty, 1 angstrom plus or minus 1 angstrom, about that over here on this. You like to fit the background, not just at a point out here, but in the wide energy range here, from about 30 eV. So right around here from the peak, 30 eV down, and as far as it goes until you get to another peak or your spectrum ends. For the next sample, which is sample number 2, we have nickel deposited on top of this gold sample. Spectrum is here, and now, as expected, we have gold now at deeper layers, and it's maybe about 10 angstroms, from about 10 to 20 angstroms, like this. That's about it, 10 to 20 angstroms. It's buried here, and it fits again very nicely over a wide energy range. The third sample, we have more nickel on top. Now the spectrum is more noisy because the signal is smaller. And again, we vary the end depth here and the start depth. You can also do it here. So that's about from 20, maybe 25 to 35 angstroms. You can also do this automated. I'll return to that in the next video.